Welcome to our lecture on instrumental variables, or more specifically, on the classic linear homogeneous coefficients model. We will have a later lecture on the local average treatment effects model that connects to this one and also talks about instruments. So today I'm going to begin with a very quick review. The presumption here is that you already know something about instrumental variables. So I'm going to focus today on showing you how to implement IV in R, in particular how to run two-stage least squares. And I'm going to give you a series of self-directed exercises that will help to really deepen your understanding of what's going on under the hood, and also explore some slightly more challenging theoretical ideas about how IV works. So let's recall the classic linear IV model. And of course, you should always read my blog. In particular, you should read the rant that I link to on the bottom of this slide about the use of error terms in econometrics and how sometimes people are kind of sloppy in their notation and how they talk about them. So here on this slide, I'm not going to be sloppy. I'm using some special notation that I like that other people don't always use. So I'm writing on the top line of the slide, I actually write y gets alpha plus beta x plus u, which is kind of like an R command rather than an econometric model, because I'm trying to show you that what I have in mind here is a linear causal model. So what I'm saying here is that x causes y, and in particular, increasing x by 1 unit increases y causally by beta units. So this is a homogeneous coefficients model. So these alpha and beta things that we see here, they're constants. They don't vary across individuals. And in this particular example, x, y, and z are things we can observe, and u is something that we can't. So on the right-hand side of this slide, I've got a little directed acyclic graph. You remember those, perhaps, from our lecture on bad controls, when we looked at selection on observables. So in this little DAG that I've drawn here, this is the prototypical DAG for IV regression. The idea is that U is a confounder, something that it's a common cause of both X and Y, but that U does not cause Z, nor is Z caused by U. So we have this common cause U. We also have z, which is this other variable. It's not x and it's not y, but it causes x. But this z does not cause y directly. It only causes y indirectly through its effect on x. And that's what I've drawn in the DAG. We'll actually talk about that DAG in some more detail in the late lecture. So for today, I just wanted to sketch it for you. Now, the example that I have in mind, and the one that you're going to analyze at the very end of this lecture in one of the exercises, is as follows. Let's say y is some kind of a measure of the career success of a musician. So what causes success? We know that successful musicians often get really positive expert reviews in the press, but they're also usually talented. So we might think that there is some kind of unobserved variable u that we could call talent. And talent, we think, should probably cause success. And talent should probably also cause favorable reviews. I mean, at least if the reviewers really know what they're talking about. So if we wanted to learn the causal effect of the reviews themselves, in other words, we're imagining some kind of a counterfactual where we were able to manipulate who got positive preference reviews and who didn't, holding all else constant, that would be the causal effect of the reviews. Well, the trouble is, if we've got observational rather than experimental data, talent is a confounder. So at the end of the lecture, we're going to think about a possible instrumental variable that could help us to sort out this problem. But in the meantime, let me write this model in a slightly more traditional way. And did I mention that you should read my rant about the error term in econometrics? If you haven't done that already, you could always click out the link at the bottom of the slide. So the more traditional way of writing this model is as follows. Y equals alpha plus beta x plus u. Covariance between z and x is not 0. Covariance between z and u is 0. So here, x is correlated with u. So we're saying we think that, in fact, the expert reviews might be correlated with talent. So that covariance between x and u is not 0. So we say that x is an endogenous regressor. The instrumental variable's relevance assumption is that the covariance between z and x is not 0. So we're trying to find some variable that is correlated with expert reviews. But the instrumental variable exogeneity assumption is that the covariance between z and u is 0. So we would be trying to find something that is not correlated with talent, but is correlated with expert reviews. If so, then that z is a valid and relevant instrumental variable. It's an exogenous and relevant IV. So this is, again, just a review. If we were to run OLS, ordinary least squares, a regression of y on x, then in large samples, our OLS estimator would be approximately equal to this thing, beta OLS. That is the population OLS slope. So that's the OLS estimand, the parameter in the population that we are estimating when we run OLS. That thing is equal to the covariance of x with y divided by the variance of x. And a familiar calculation with covariances and plugging in our model, our causal model for y, shows that the OLS estimand is equal to beta. That's the true causal effect of x on y, the effect of increasing x by 1 unit on y. It's equal to that beta plus something else. So that something else is it's actually the slope of a regression of u on x. So it's the covariance of x with u divided by the variance of x. So in the example I was mentioning before, that would be like, imagine you could observe talent. This would be a regression of talent on expert reviews. So if x is exogenous, I should say that's actually a typo on the slide. So it should say if x is endogenous, then the covariance between x and u is not 0. So again, there is a typo on the slide. Apologies. If x is endogenous, then the covariance between x and u is not 0. And so beta OLS is not the same thing as the true causal effect beta. Now, if we turn our attention instead to the right-hand side of this slide, we can see the instrumental variables estimand, beta IV. That is the thing that in large samples, our IV estimator will be approximately equal to. It is the population quantity that we are estimating when we do IV. So you probably recall that this is the covariance between z and y divided by the covariance between z and x. So again, plugging in the causal model for y and doing a little bit of manipulation, we get a familiar expression, namely that beta IV is equal to beta, the true causal effect of x on y, plus the covariance between z and u divided by the covariance between z and x. Now, this whole idea of dividing by the covariance between z and x is a complete non-starter if z and x are uncorrelated, because we can't divide by 0. So we definitely need the covariance between z and x to be not 0. So if that's the case, then we can form the IV estimand. We can take that ratio. And if we are able to form that ratio, then we see that beta IV will be equal to the true causal effect beta precisely when the covariance between z and u is 0. In other words, when the instrument is exogenous. Something else that's kind of fun to notice is if z were not an exogenous instrument, if it were actually endogenous, so if the covariance between z and u were not 0, then sort of the weaker that its correlation with x is, then the farther beta IV is from beta. That's kind of an interesting thing to think about if you've ever considered weak instruments. This is not exactly a weak instrument consideration, but the point is that when the relationship between the instrument and the regressor is not strong, that magnifies the effect of having an invalid instrument, of having an instrument that's actually endogenous. But today, we're not going to worry about any kind of endogenous instruments. Z is a pristine, perfect, relevant, and exogenous instrument. And if so, it can solve this endogeneity problem very easily. Now, it is common to decompose this estimand into two pieces. And one of the reasons it's common is because at the moment we're just looking at a very simple case where there is a single endogenous regressor in a single instrument. But of course, as you know from your intro econometrics course, there are many other more interesting, more complicated situations that have multiple instruments or maybe even multiple endogenous regressors. So before we get there, let's just stick with the simple model and let's introduce some more terminology that you may be familiar with. So we can always rewrite this IV estimand by using one of my favorite tricks, which is to multiply by 1 for a clever choice of 1. So my clever choice of 1 at the top of this slide is going to be variance of z divided by variance of z. I hope you'll agree with me that that is indeed 1. And if I multiply the instrumental variables estimand by that thing, then I will get a ratio of 2 fractions. The first fraction is the covariance of z with y divided by the variance of z. Now, what's that? Well, that is the slope from a population linear regression of y on z. In the denominator, we have the covariance of z with x divided by the variance of z. Hey, what do you know? That's another population linear regression slope. This time, it's the slope of a population linear regression of x on z. So let's give the numerator a name. Let's call it gamma 1. And let's give the denominator a name. Let's call it pi 1. So we'll call gamma 1 the reduced form coefficient. This is, again, it's the slope from a regression of the outcome on the instrument. And let's call the denominator the first stage coefficient. That is, again, the slope from a regression of the endogenous regressor on the instrument. So we could indeed write these regressions out. We could write out the reduced form regression in full. And, we all know the basic rules for linear regression, so we can work out what would the intercept be in that regression. Well, I'll call it gamma naught, gamma 0. What would the slope be? And if you haven't done so already, you should definitely go read my rant about the error term in econometrics, because here I'm being very scrupulous, and I'm pointing out that in the reduced form regression, I am defining epsilon to be y minus gamma naught minus gamma 1z. Epsilon is not something that exists out there in reality. Epsilon is kind of an artifact of a particular model that I wrote down, a particular way I've defined gamma naught and gamma 1. And the way that I'm using my notation on the slide is intended to make that clear. So I write epsilon is defined as y minus gamma naught minus gamma 1z, where gamma naught is defined as follows, and gamma 1 is defined as follows in terms of functions of the data. Covariances, variances, and means. And once I've defined all that stuff, then it is a tautology, then it is just true by definition that y is gamma naught plus gamma 1 z plus epsilon. And it is also true by definition, and if this is a little unfamiliar to you, you could check it, that the expectation of that epsilon is equal to the covariance between z and epsilon is equal to 0. I can do the same exact thing for the first stage. My notation is now different. I will call that sort of first stage error term v. And again, v is something that I define. So there's not some kind of assumption about v or epsilon. These are just properties that follow from the way that I have defined pi naught, pi 1, and v. Once I've defined them, then I can write an expression for x. I can write that x is equal to pi naught plus pi 1z plus v. And again, that is a tautology. It's something that is true by definition. Given the way I've defined all the terms, given the way I've defined the pi's and the v, this relationship holds for free. And in addition, the expectation of v is 0, and so is the covariance between z and v. Okay, so why am I doing all of this? Well, I want to write down some things that look like linear regression models, because in a bit we're going to be simulating from an IV model, and we will need to think about how to do that. So, suppose that z is exogenous. Well, I've now defined this v on the previous slide. So what is the covariance between u and v going to be? Well, the covariance between u and v is the covariance between u and, remember how I defined v on the previous slide, it was x minus pi naught minus pi 1z. Okay, so using my favorite rules for covariance, what am I going to end up with? I'll have the covariance of x with u, covariance of u with minus pi naught? Well, pi naught is a constant, so that's 0. What about the covariance between u and minus pi 1 z? Well, pi 1 is a constant. I could pull that out. And z is uncorrelated with u. So I end up with the covariance between x and u. In other words, if we think about the source of endogeneity that we began with here, so in the example, it's the correlation between the expert reviews, x, and talent, u, that is exactly the same thing as the correlation between u and v. The correlation between talent and what is v? Well, v is the component of expert reviews that is left over when we use a linear regression with z to predict talent. So v is the part of talent that can't be predicted from our instrument z. And the point here is that this means that we can write our IV model as a system of two equations, which you have seen perhaps in many textbooks, but oftentimes the textbooks will begin with these equations. I like to work backwards because I want to start with what we assume and what's in the data, and then I want to find out what models I'm allowed to write down based on how I've defined things. So we can write y equals alpha plus beta x plus u. That's our causal model. And we can also write x equals pi naught plus pi 1 z plus v. That is not a causal model. That is a tautology. It's true by definition, given the way we've defined pi naught, pi 1, and v. Did I mention that you should read my blog post on the error term in econometrics? If you haven't done so, now's a great time. So this system of two equations is such that u and v, they're actually correlated with each other, but u and v are both mean 0, and the covariance between z and v is 0. So this is all by construction. And now we are ready to simulate from an IV model using these two equations that we've just come up with. So how are we going to do it? Well, step one will be to generate our instrument. We can generate it however we want. The next step will be to generate correlated errors u and v that are going to be independent of z. So we're going to generate these errors u and v. They need to be correlated. That was the point of doing all that algebra on the previous slides. Didn't just do it for my health, although it does keep me young. We're going to generate u and v to be correlated with each other, but independent of z. Once we've done that, we're home free. We're able to just create some linear regression equations and use them to generate x and y. So we will set our coefficients pi naught and pi 1. And we'll set our causal model coefficients alpha and beta. And then we can just generate x first. So x will be pi naught plus pi 1z plus v. And then y will be alpha plus beta x plus u. So of course we've got to generate x first because we need to then use x to generate y. We could generate z any way we like. You can choose your favorite way of generating it. One really simple thing that we could do is that we could generate z to be a standard normal independent of u and v. Now, for u and v, there's also many options, so we need them to be correlated. One really simple thing to do, and something that builds on our lecture about the multivariate normal distribution, would be to simulate u and v from a bivariate standard normal distribution with correlation rho. That's not the only choice you could make, but that's a simple one. So that's actually what I'm going to ask you to do in the next exercise. So this is a fairly meaty exercise. All the exercises in this lecture are fairly long. So please take the time to work through this exercise carefully and check your solutions against those on the course website. There's a lot of really interesting material in these exercises, and I think that working through them carefully will really deepen your understanding of IV. All right, so now that we've tried our hand at some exercises, and now that we understand how to generate from an IV regression model in R, let's look at something a little simpler. How do I just run two-stage least squares in R? What is the command for that? Okay, so we're now going to be talking about a more elaborate example. And I still want to keep it relatively simple just to avoid getting too bogged down. So I'm sure you've seen more interesting examples than this in textbooks and papers, but here is one that I will use that's complicated enough to show you everything you need to know about running two-stage least squares in R, but simple enough to avoid cluttering up the slide. So I have two equations. The first one is a linear causal model. So y is caused by x, w, and u, and our goal is to learn the causal effect of x, which is beta 1. In this equation, it's always good to ask yourself what's constant and what's random. So here, y, x, w, and u are random, and the betas are constants. So this is, again, a homogeneous coefficient model. It's a model where everybody in the whole population has the same causal effect, beta 1, and therefore that's just a constant. So x is our endogenous regressor. It is correlated with u. And for fun, I've added in an exogenous control regressor w. So w is some other thing in here that is actually another thing that is uncorrelated with u. Now the x equation, that is not a causal model. That is a population linear regression. So that is something that is, again, a tautology. It's something that holds automatically once I define those pi's in the right way. I define them to be regression coefficients. And if I do that, then it's going to be the case that z1 and z2 and w are all uncorrelated with v. So what are z1, z2, and w? Well, w, again, is that exogenous control regressor, the one that's not correlated with u. And z1 and z2 are two instrumental variables. So you could be in a situation where you have one endogenous regressor x and two instrumental variables z. That's what I have here. So in this model, the instrumental variable's relevance assumption will be that at least one of, oh my, I've discovered another typo. The relevance assumption will be that at least one of pi 1 and pi 2 is non-zero. So the slide says pi naught. Sorry about that. That's a typo. So relevance is that at least one of pi 1 and pi 2 is non-zero. Exogeneity is that z1 and z2 are both uncorrelated with u. Okay, so what is two-stage least squares? Well, it's least squares carried out in two stages. So you could do it, quote unquote, by hand, and if you were to carry out that procedure, here's what you would do. In the first step, you would regress the endogenous regressor x on both of the instruments and the exogenous regressor w. You would then save the fitted values from the regression. In the second step, you would regress y on those fitted values x hat, the ones that you created in step 1, and the exogenous regressor, the control w. The coefficient on x hat will then be your estimate of the causal effect of of interest. And if you do this procedure, you will get exactly the same point estimate as if you use a canned IV, or rather I should say a canned two-stage least squares command. However, you will not get the correct standard errors. I'm not going to get into the reason why right now. You may know that if you have taken an econometrics course that talks about generated regressors. So in a moment, we're going to use a package that will give us the correct standard errors. Another thing that may be interesting for you to think about is that in a model with a single endogenous regressor and a single instrument, two-stage least squares is equal to the simple IV estimator that we looked at earlier in the slides, but it's also equivalent to what is called a control function approach. And again, you should always be reading my blog because I put all my best stuff there. So you can click on this link to 3 ways of thinking about instrumental variables for some more discussion. And when you read that, you may, in fact, notice some items that appeared in some of your exercises. All right, so here is the command for two-stage least squares in R. It is not available in base R. It is not available automatically when you load R. You need to install a package. So the package you need is called ivreg, And the function you're going to use is also called ivreg. There is a link on the slide here where it says the ivreg function. If you click that, you will be taken to the package vignette that talks about this ivreg package. It carries out two-stage least squares estimation. It calculates the correct standard errors. For today, we're going to keep life simple and just assume homoscedasticity. In a later lecture, I will show you how to get heteroscedastic consistent standard errors. And as I mentioned in my earlier lecture on logistic regression, in this course, I like to teach you tools that play nicely with other tools. And ivreg plays nicely with tidy, augment, and glance from Broom. If you want to find out some more about that, you can click on the link on the slide that says See Here. So here is the syntax for ivreg. ivreg, then you put your formula, comma, and then you say data equals, and you put in the data frame. And I noticed, again, this is embarrassing, but this slide has another typo, so there should not be a parenthesis here. I will remove that, and I will correct it on the course website. Apologies. So this parenthesis that I am highlighting should not be there. Okay, what does the formula syntax look like? Well, the formula syntax, it has two pieces. It has the causal model formula, then this vertical bar, and then the first stage formula. So on the slide, I have an example of that. The first stage formula is what is called one-sided. That means there's no left-hand side variable and there's no tilde. But the causal model formula is a standard R formula of the kind that you've seen when you use LM. So for the running example that I have been discussing on the past few slides, the formula that we would use is y tilde x plus w, vertical bar, z1 plus z2 plus w. So let's take a look at the first stage formula. What's going on here is we use plus to separate the different right-hand side variables. So those are the predictors of x in the first stage regression. Notice that I've got to specify what the instruments are, but I've also got to put in the exogenous control regressor. I have to put it in manually. And if we turn our attention to the formula chunk that is to the left of the bar over here, that's the causal model formula, and that looks familiar. That's y, our outcome variable, tilde x plus w. One slight comment, besides the fact that this parenthesis shouldn't be here, you'll notice that in my ivreg command, I write data equals, and then I specify the data frame. You actually need that. You actually need to specify data equals. If you don't, you're going to run into a problem. That's because by default, the second argument of ivreg is something else, and it's something else that we don't need. So make sure that you specify data equals, otherwise you will have an error message appear that might confuse you. That is different from LM. With LM, you can get away with not specifying data equals because the second argument of LM is the data frame. And now it's time for a substantial additional exercise for you. So please pause the video and spend the time that you need to work through this. You will need to generate draws from a more complicated distribution. And as always, you can check your solutions against those on the course website. In the final part of this lecture, I would like to show you an empirical example. This is based on the example that I described at the beginning of the lecture. Or rather, the example I described at the beginning of the lecture is based on this empirical example. So this is from a paper by two authors, Ginsberg and von Ors. This was published in 2003 in the American Economic Review. To download a copy of the paper, you can click on the link at the bottom of the slide. They ask the question of whether expert reviews cause success, or maybe, in fact, expert reviews have no effect on success, and it's just that talent, which is kind of an unobserved confounder, causes both success and favorable press reviews. So they used data from the Queen Elizabeth with an S, so not Queen Elizabeth from England, Queen Elizabeth piano competition. You can click on this link to read a bit about it. And what's interesting about this piano competition is that the performers all appear in random order. And perhaps surprisingly, judges end up giving higher rankings to musicians who perform later in the performance order. So the first stage here is that we really are randomly assigning performers to who goes first, second, third, fourth, fifth, and so on. But somehow that randomly chosen order actually affects the rankings that judges give. So what this paper does is it estimates the effect of judge rankings on subsequent career success. So the idea here is that the judge ranking is an expert review. So that's kind of like an expert's judgment of each performer's quality. And here the performance order is going to be an instrument for the judge's ranking. And because that instrument is randomly assigned, we might think that we're out of the woods and we've got the IV exogeneity condition. Well, that's not quite right. So the fact that it's randomly assigned is definitely helpful. In this case, the IV exogeneity assumption would be that has sort of two parts. One is that the order, the performance order, is independent of talent. Well, that we get for free because if talent is like a pre-existing characteristic and we've randomly assigned the order of performance, then it's not going to be the case that the earlier performers are more or less talented than the later. It's random every year. But there's actually a second thing we need. It's something that the DAG representation of an IV model makes more explicit. We need there to be no direct effect of ranking on success. Now, that's a little bit complicated to think about. How could there be a direct effect of ranking on success? I will leave that for you to ponder, and there is some discussion of that in the solutions to the exercise. So to load the data, which interestingly enough, it took me a long time to locate this data set, but I did eventually find it on some obscure website, and I wasn't sure that it really came from this paper, but then I replicated everything, and all the numbers matched. So indeed, this is the data set from that paper. So this is a data set with 132 rows. Each row is a performer, so a pianist who competed in this competition in one of the years that were listed. And the columns, well, there's a number of columns that I'll describe in a moment. You can load this data set from my website. Here is the URL. And now let me tell you what those columns are. So first we have, on the left-hand column here, we have some instruments / exogenous regressors. We've got year of birth of each competitor. We've got the year of the competition. Remember that this was, this did not just use data from one year of the competition, it used data from many years. We have the ranking by the jury. So the jury is ranking the competitors from 1 to 12. There are 12 competitors in each year. Order is the random order of appearance in the competition, also 1 to 12. Age is the age at the time of performance. Belgium is a dummy variable for whether the pianist is Belgian. The reason that they have that variable is because the competition takes place in Belgium, and there might be some kind of home bias, perhaps. USSR is a dummy for a USSR pianist. I imagine that that's here because you might worry that at the time there was some sort of global politics playing a role. It might be biased against Soviet pianists. A dummy for a USA pianist. I don't know why that's there. Maybe everyone dislikes Americans. And of course, a dummy for a female pianist is female. So then the outcomes here, there are actually multiple different measures of success that the authors considered. Critics is sort of success ranking as critical reviews later in your career. BLL is the number of records in the BLL catalog, which is the Belgian Listening Library. GCCD is records in the gramophone classical catalog or the diapason catalog. These were, I think that these publications do still exist actually, but they may be less relevant today now that lots of things are online. But at one point, these were big sources for kind of learning about different classical music albums that were available. And then present is the number of catalogs in which this particular person is present. So these are kind of measures of their later success in terms of how critics view them, how many records they made, and like how many catalogs those records are available in. And now we have come to the end of the lecture, and it is your turn to analyze the data from this paper and see what you find. So for this particular exercise, you will only need the columns critic, order, and ranking from this QE Tibble that you can download as I showed you before. Of course, you are welcome to replicate the whole paper, and indeed, that could be quite a fun exercise for you. So work your way through these items and then have a look at the solutions on the course website. I think this is an interesting example to think about very carefully, and it's also one that I have never seen anyone use in an econometrics course before. So there's a first time for everything, and I hope you enjoy this slightly unusual exercise. At least it's not the returns to education.